Good morning, students. Myself, I am Dr. S.P. Yeole, HOD, Chemistry Department, SDSM Junior College, Palkar. Students, in previous lecture, we discussed about some topics of polymer chemistry. In that introductory part I gave, in that we turns towards classification of the polymers. Basically, polymers are classified into six types on their properties. In last lecture, we finished the three topics like first one classification of polymers on the basis of source or origin. Second type, we discuss classification of polymers on the basis of structures. And thirdly, classification of polymers on the basis of mode of polymerization. Rest of the three classification we discuss today only. Students will see that fourth classification has the name of that classification of polymers on the basis of intermolecular forces. You know, intermolecular bonding like that, intermolecular forces there because bonding is due to what forces or force between the two atoms or molecules. That is simple definition. As per that, these polymers also base on their intermolecular forces. You see slide in that at center side we'll see intermolecular forces. So they comes either by elastomers, then from that we'll get fibers. Then top side you can see thermoplastic polymers and downside we'll see thermosetting polymers. These four sub classifications are there and that we'll see in detail one by one now. First of all, we'll see elastomer. In this picture, we'll see some rings are there, some barrels are there, and this one is also some instruments and some material which are regarding the elastomers. In elastomers, we see the elasticity of the molecules or elasticity property by which a substance gets stretched by external forces and restores its original shape on release of that forces that causes elasticity. Then elastomer, second point we'll see elastomers, the elastic polymers, they have weak van der Waals type of intermolecular forces which permit the polymers to be stretched. This weak, by that we can stretch up to the long distance also. That's why these are weak forces so important. A few cross links between the chains which are help stretch polymers to retract to its original position on removal of applied force that you can observe by simple rubber also. For example, vulcanized rubber, Buna ice rubber, Buna N type of rubber, neoprene, etc. All these are examples of elastomers. Now next slide we'll see about the fibers. Fibers means basically one rough idea in your mind is that threads. So various types of threads we'll see in this picture, and these threads that different color we can give. Color is not the matter over here, but fibers that we can get. So fibers we can get. These are obtained by polymeric. These are polymeric solids which can form the threads, and these threads are called as fibers. Some are calling that fabrics also. The fibers possesses high tensile strength, means their toughness is high, tenacity is high, which is a property to have resistance to breaking under tension. That type of materials or solid material is also one of the fiber. Second point we'll see their characteristics. This characteristics is due to the strong intermolecular forces like hydrogen bonds or bonding, and they possess strong dipole dipole forces or strong dipole dipole interaction. By that also we can get some fibers. Next one is that They can be formed due to strong intermolecular forces, which are the fibers are crystalline in the nature, and that type of fibers we are getting. Some examples I am giving. That is of polyamide, means nylon double six. Why double six is there? That we discussed in previous terms. Then polyesters, terylene. These are the fibers which are polymeric solids. Then next one is the thermoplastic polymers. Thermoplastic polymers diagram you can see. So what kind of material we can get by this fiber? In diagram you see this blue color is the, you may say, crate which are using for the milk and that vegetables and that. Later on, these stuffs which are useful in the laboratory also, as well as in the household purposes. These are molded. So here some are, we'll see, some are obtained by heating and some are by remolded, and that's why these are called as heated and remolded. 100% or 100s of the uh, thermal or time set can also be recycled. Recycle means we can get the new type of same fiber also by breaking. Then plasticity of this fiber is the property of being easily shaped or easily molded. Molded polymer, these are very important, and nowadays these are required in your household purposes. Thermoplastic. Thermoplastic polymers are capable of repeated softening on heating and hardening on cooling. You know, these properties are very important. They plays the role in making of the thermoplastic polymer. These polymers possesses moderately strong intermolecular forces that are intermediate between elastomers and fibers. So, what are the properties of this one? These are ranging between these two types, elastomers and that type of intermolecular forces. That's why that's what ranging between the these two fibers. Example: polythene, polystyrene, etc. These are examples of thermoplastic polymers. Next slide is what thermosetting polymer. Thermosetting polymers. So these polymers are thermosetting polymers are rigid polymers, and during their formation they have property of being shaped on heating, but they get hardened while hot. And by this we can get such type of instruments which are shown in diagram. We'll discuss later also. Once these fibers are hardened, then this fiber becomes infusible and they cannot be softened by heating, as well as they cannot be remolded also. Later on, as per the characteristics, this characteristic of this fiber is a result of extensive cross-linking by covalent bonds which are formed in the molds during hardening or setting process while hot. For example, they give bakelite, urea formaldehyde, resin, and by using such type of fiber or by using such thermosetting polymer, we can get such type of products. This first one, second one, this third one. Okay, so these fibers will get with the help of thermosetting polymers or thermosetting fiber. Later on, we'll discuss the next type is that next type of classification of polymer, which depends on the basis of type of different monomers. So distinguishing also we can study. In that, main two important terms are there: homopolymers and copolymers. So first of all, we'll see what do you mean by homopolymer. Homopolymers are those which are which have only one type of repeating unit, and these repeating units are called homopolymers. Homo means same. Same kind of material whenever using for polymerization. So by that we can get the homopolymer. Usually these polymers are formed from the single monomer. In some cases, the repeating unit is formed by condensation of two distinct monomers. For example, they said polythene, polypropylene, nylon 6, polyacrylonitrile, nylon double 6. So these are examples of the homopolymers. Copolymers, next type is in copolymers. These polymers which has two or more types of repeating units are called copolymers. These polymers are formed by polymerization of two or more different types of monomers in presence of each other. The different monomer units are randomly sequenced in the copolymer. For example, Buna S and Buna N type of fibers are the best examples of copolymers. Later on, next type of classification we'll see the classification of polymers which depends on the basis of biodegradability. Now, degradability that you can understand which are easily destroyed and biodegradability which are easily destroyed and that can be matches or goes to the nature. Now, biodegradable polymers are special type or special class of polymer that breaks down after its intended purpose by bacterial decomposition processes to result in the natural byproducts such as gases, carbon dioxide into nitrogen, water, biomass, and inorganic salts. So these are the best examples of the biodegradable polymers. Next one is the non-biodegradable polymers. The term non-biodegradable describes polymers that do not break down to a natural, environmentally safe condition over time by biological processes, and most plastics are non-biodegradable mainly because of plastic is widely used because of its low cost, versatility, and durability. So these two types we'll see under this one biodegradable and non-biodegradable. Now next one table or next slide indicates that polymers how they classify. Now we'll see right from beginning. Based on the sources, next type is based on the structure, then biodegradability, then based on reaction mode of polymerization, then based on molecular forces. Now from this type we'll see one by one. The polymer which are based on the sources, in that natural polymer example star cellulose, then semi-synthetic polymer example rayon, synthetic polymer example nylon and polyester. These core types or subtype that you can study. Second type is based on structures. On structure, we'll see linear polymer, that is nylon and polyester, branch and polymer PVC and Teflon, cross-link polymer bakelite and melamine. Later on, biodegradability. On that basis, we'll see biodegradable polymers like nylon 2, nylon 6, and nylon biodegradable, that is what non biodegradable, that is of plastic. Next type we'll see which depends upon the reaction mode of polymerization. In that addition polymer, in addition polymer we'll see homopolymer, polythene, poly, polypropene. Next one is the copolymer like Buna S, and later on condensation polymer. In that example we'll see nylon double six and polyester. Then this classification last one depends upon based on molecular forces. First type is elastomer, example neoprene, isoprene, fibers like nylon, polyester, thermoplastic polymers like PVC, polystyrene, thermosetting polymers like bakelite and melamine. So such type of classification we can study under polymers. This table, this chart is very important. Later on, we'll discuss some important polymers like what rubber, polythene, Teflon, polyacrylonitrile, polyamide polymers, then polyesters, phenol, formaldehyde, and related polymers, Buna S rubber, neoprene, viscose rayon. So these are the related some important polymers. Later on, we'll see the topic of rubber. Rubber regarding elasticity. When you're going to use any kind of rubber, that might be rubber band, or that might be flexible balloons, and that almost they are related with the elasticity. About that, we'll see. First of all, elastomers are popularly known as rubbers. For example, balloons, shoe soles, tires, surgeon gloves or surgical gloves, garden hose, pipes, etc. are made from elastomeric material or elastomeric rubber. Example, they said isoprene that can be obtained by CH2 double bond CH, then CH3 double bond CH2. So that is the structure of isoprene. Later on, natural rubber. Natural rubber includes or contain monomers of the natural rubber is isoprene. Just I told, its IUPAC name is 2-methyl 1,3 butadiene. Two times double bonds are there, that's why butadiene. And totally four carbon atoms are there. The natural rubber is a high molecular mass linear polymer of isoprene. Its molecular mass varies from uh, 1,30,000 unified mass to the 3,40,000 unified mass. That is the number of monomer units which are varies from 2,000 to 5,000. And about that, we'll see the natural rubber. In natural rubber, we'll get the final product is of poly 2-methyl 1,3 butadiene or polyisoprene. Later on, properties of natural rubber. Polyisoprene molecule has cis configuration of the carbon-carbon double bond, and it consists of the various chains which are held together by weak van der Waals forces and has coiled or coiled structure. And later on, it can be stretched like spring and exhibits elastic property. Now, how we can get this one? Polyisoprene we can get from the isoprene. You see isoprene structure. First of all, top side I said this isoprene. Same isoprene we'll see in the repeated form. We can take in the repeated form over here. Then CH2 double bond C, CH3 downside. Then top side CH double bond. Then this CH, CH. It can be undergoes polymerization with the help of Ziegler-Natta catalyst. Remember this term. It is the type of catalyst which is useful and important for preparation of polyisoprene. Whenever isoprene undergoes polymerization, actually here below reaction you can note polymerization. Top side we can get Ziegler-Natta catalyst, but downside you can write polymerization. Okay. Later on, by polymerization we'll get here CH3 CH2 double bond CH2 n times. Actually, in this reaction, before starting of the isoprene, before starting of the isoprene, here we have need of small n. Here small n is required. Means n molecules of isoprene when it undergoes polymerization in presence of Ziegler-Natta catalyst. So we'll get number of the molecule. This n small n shows what number of the molecules of the isoprene. That's why it is called as what polyisoprene. Remember this term. So this is the preparation of polyisoprene. Later on, we can get the next topic, that is of vulcanization of rubber. Now we discuss about the vulcanization of rubber. In vulcanization of rubber in this slide, you can see some diagrams. In the diagram, you see uh, some related terms are there that we can discuss later on. Before that, you see here, what do you mean by vulcanization? Vulcanization is one of the type of polymerization. So it is the process by which network of cross-link or cross-linking is introduced into an elastomers, and that process is called as vulcanization. Vulcanization improves the physical properties of the natural rubber as well as the process of vulcanization that can be carried out basically in 1839 by Charles Goodyear, which is the which is an American inventor who invented the process of vulcanization. Now, the profound effect of vulcanization enhances means increase the properties like tensile strength, stiffness, elasticity, toughness, etc. of the natural rubber. Because natural rubber directly we cannot use for making of tires or tire cord. So this rubber is not processed by this way. That is what vulcanization. For that, one important ingredient is required, that is of sulfur. So sulfur vulcanization is the most frequently or effectively can be used for this process of vulcanization. Now sulfur form cross-linking between the polyisoprene chains which results in improved properties of the natural rubber, and that's why sulfur has the best and very important role in vulcanization. Vulcanization can be carried out by heating raw rubber with sulfur powder. Raw rubber means that rubber can be obtained from the latex of the rubber tree, and that in presence of some organic compounds, these are called as accelerators that about 150 degrees Celsius. And the most effective common accelerator is of ZBX. So ZBX has the long form zinc butyl xanthate is one of the most important accelerator for vulcanization. What does it accelerate? It accelerates to get the cross-link chain by the sulfur, and that's why the increasing amount of the sulfur in the chain of rubber that can be hardened, and due to hardening we'll get the better quality rubber. For example, when the amount of sulfur is raised in the process about 40 to 45% is a non-elastic hard material that called as ebonite, and that ebonite can be obtained. In diagram we'll see such type of products are there in which ebonite rubber can be useful. Later on, one or more sulfur atoms are cross-linked to polyisoprene chains, and in that by cross-linking, opening of the double bonds and produces three-dimensional vulcanized rubber, and this process of the vulcanization rubber can be completed. You can see in diagram also what products we are getting by vulcanization of rubber. Students, up to this one we study today. In next lecture we'll start from polythene. Take care. Stay safe. Thank you.